Welcome! In this session, we'll explore LeetCode problem number 1031, maximum sum of two non-overlapping subarrays. This problem challenges us to efficiently calculate the maximum sum of two subarrays with specified lengths, ensuring they do not overlap. Let's dive into the details and approaches to solve it. In this problem, you're given an integer array called nums, along with two integers, first len and second len. Your task is to find the maximum sum of elements from two non-overlapping subarrays of lengths first len and second len. Now, a subarray is simply a contiguous segment of the array, and the key requirement here is that the two subarrays you choose cannot share any indices, they must be completely separate from each other. The array nums can contain both positive and negative numbers, and its size can range from 1 to 1000. Similarly, the lengths of the subarrays, first len and second len, are both guaranteed to be at least 1 and at most 1000. The result you return should be a single integer, representing the maximum possible sum of the two non-overlapping subarrays of the specified lengths. Let's look at a few examples to understand this better. In the first example, the input array is nums equals 065225194, with first len equals 1 and second len equals 2. One optimal solution is to select the subarray 9 of length 1 and the subarray 6, 5 of length 2. The sum of these two subarrays is 9 plus 6 plus 5, which equals 20, so the output is 20. In the second example, with nums equals 3813211890, first len equals 3, and second len equals 2, the best choice is the subarrays 3, 8, 1, and 8, 9. Adding their elements gives 3 plus 8 plus 1 plus 8 plus 9, resulting in a maximum sum of 29. Lastly, in the third example, for nums equals 2156095038, first len equals 4, and second len equals 3, the subarrays 5609 and 38 yield a total sum of 31, which is the output. Now, let's discuss some constraints and important notes. First, the lengths of the subarrays, first len and second len, are both between 1 and 1000. Additionally, the sum of these two lengths must be less than or equal to the total length of the array nums, which has a minimum size of 2. Each element in nums can range from -1000 to 1000. It's crucial to remember that the two subarrays must be non-overlapping, meaning they cannot share any indices. For instance, if first len is 3 and second len is 2, the subarrays cannot overlap in any way. The goal is to maximize the sum of the two valid subarrays, so your solution needs to account for all possible placements of the subarrays to find the highest possible sum. To tackle the problem of finding the maximum sum of two non-overlapping subarrays, we considered multiple approaches. The first is the brute force approach. The idea here is straightforward: iterate through all possible subarrays of lengths first len and second len, ensuring they do not overlap. For each combination, compute their sums and track the maximum result. While this guarantees accuracy, the computational cost is high. With nested loops to explore all valid pairs, the time complexity becomes n squared asterisk max, first len, second len, which makes it impractical for large inputs. On the other hand, a more efficient approach involves using a sliding window combined with prefix sums. By pre-computing cumulative sums, we can calculate subarray sums in constant time rather than recomputing them repeatedly. This method involves iterating over the array twice, once with first len as the left subarray and second len as the right, and once swapping their roles. The overall complexity is reduced to n, making it much more scalable. While the sliding window with two pass prefix sums is efficient, it does come with trade-offs. It requires careful management of prefix sums and the indices controlling the sliding window. Another alternative is an optimized sliding window approach that avoids prefix sums altogether. Instead of pre-computing cumulative sums, we dynamically maintain a rolling maximum for one subarray while iterating over the other. For instance, as we iterate through the second len subarray, we keep track of the maximum sum of a first len subarray to its left, and vice versa. This method also achieves n complexity, but the logic can become more intricate to implement and debug. Ultimately, after evaluating these methods, we chose the two-pass prefix sums approach as the most balanced solution. By leveraging prefix sums, we can compute subarray sums quickly and avoid redundant calculations, while iterating twice ensures all valid configurations of non-overlapping subarrays are considered. This approach is efficient, easy to understand, and straightforward to debug. The primary reason for selecting the two-pass prefix sums approach is its balance of efficiency and simplicity. The brute force method, while conceptually simple, is computationally too expensive for larger arrays due to its n² complexity. Meanwhile, the rolling maximum approach avoids the memory overhead of prefix sums but introduces extra complexity in managing dynamic sums, which can make debugging harder. The two-pass prefix sums method strikes the right balance. Although it requires additional memory for the prefix sums array, this trade-off is justifiable because it simplifies the logic and reduces the chances of errors during implementation. By combining sliding windows with pre-computed cumulative sums, we achieve optimal performance without sacrificing clarity. Overall, this makes the two-pass prefix sums approach the best choice for solving this problem effectively and intuitively. In this problem, our goal is to find two non-overlapping subarrays within a given array, each of specified lengths, such that their sums are maximized. To achieve this, we use an efficient approach that combines the sliding window technique with prefix sums. First, we calculate the prefix sums of the array. The prefix sum array allows us to compute the sum of any subarray in constant time by subtracting the appropriate values. This is a key efficiency gain, as it reduces the time complexity of calculating subarray sums from O(n) to O(1). By leveraging this structure, we can efficiently explore potential configurations of the two subarrays while ensuring they remain non-overlapping. To find the maximum sum of the two subarrays, we iterate over all possible positions for the first subarray of length first len. For each position, we calculate its sum using the prefix sum array. Next, we explore two regions for the second subarray of length second len. The second subarray can either be positioned completely before the first subarray or completely after it. In each region, we calculate the maximum possible sum of the second subarray. Additionally, we reverse the roles of first len and second len to account for all configurations, as the problem does not specify which subarray should appear first. Finally, we track the highest combined sum across all configurations and return this value as the result. There are a few key insights that make this algorithm efficient and effective. First, the non-overlapping constraint is managed by dividing the array into two separate regions relative to the first subarray, ensuring that the two subarrays do not overlap. Second, the use of prefix sums is critical for efficiency, as it enables constant time calculations of subarray sums. Finally, the symmetry of the problem simplifies the implementation. By swapping the roles of first len and second len, we can ensure that all possible configurations are considered without needing additional logic. These insights together form the foundation of the algorithm. The algorithm relies on a few key data structures. The most important is the prefix sum array, which stores the cumulative sums of the array. This structure allows for efficient range sum calculations and has a space complexity of O(n). Additionally, we use variables to track the maximum sums of the subarrays for different configurations as we iterate through the array. These variables are updated dynamically to reflect the best results found so far. Together, these structures enable us to solve the problem efficiently while maintaining clarity in the implementation. The algorithm involves several key operations. First, we construct the prefix sum array in a single pass through the input array. Each element in the prefix sum array is calculated as the sum of the previous prefix value and the current element. Next, we use the prefix sum array to calculate the sum of any subarray in constant time by subtracting two values. Finally, as we iterate through the array, we dynamically update the maximum sums for the first len and second len subarrays based on their current positions. These iterative updates ensure that we are always considering the best possible configurations of the two subarrays. Now, let's analyze the complexity of the algorithm. For the time complexity, constructing the prefix sum array requires O(n), and iterating over all possible positions for the two subarrays also takes O(n). Therefore, the total time complexity is O(n). For space complexity, the prefix sum array requires O(n) space, while the additional variables used to track the maximum sums only require O(1) space. As a result, the total space complexity is also O(n). This efficiency makes the algorithm well-suited for handling large input arrays. Finally, let's address some important edge cases. First, if the array length is smaller than the sum of first len and second len, it's impossible to select two non-overlapping subarrays, so the result should be 0. Second, we need to ensure that configurations where one subarray is at the very start or end of the array are handled correctly. Third, if either first len or second len is 0, the result should depend solely on the other subarray. By carefully considering these edge cases, we can ensure that the solution is robust and handles all inputs correctly. Here, we define the function maxSumToNoOverlap within a solution class. The function takes three parameters, the array nums and the lengths of two subarrays, first len and second len. Inside this function, we define another helper function called maxSum that will calculate the maximum sum for two non-overlapping subarrays of specified lengths, L and M. The first step in maxSum is to compute the prefix sums for the input array. The prefix array helps us efficiently calculate the sum of any subarray using the difference between two prefix values. Once the prefix sums are ready, we calculate maxL, which keeps track of the maximum sum of any L-length subarray that ends at or before each index. Similarly, we calculate maxM, which tracks the maximum sum of any M-length subarray that starts at or after each index. These two arrays allow us to efficiently combine the two subarrays. Finally, we iterate through the array to combine the results of maxL and maxM. For each valid position, we compute the sum of an L-length subarray on the left and an M-length subarray on the right. We update maxSum to store the highest sum found so far. The function then returns this maximum sum. Now, at the end of the maxSumToNoOverlap function, we return the maximum value between two scenarios. First, when the subarray of length first len appears before the subarray of length second len, and second, when their positions are reversed. This ensures that we account for both possible orderings of the two non-overlapping subarrays, giving us the desired result. By combining the flexibility of the helper function maxSum with this final comparison, we can efficiently compute the solution to the problem. Here, we are implementing the solution in Java to find the maximum sum of two non-overlapping subarrays. The main method, maxSumToNoOverlap, returns the maximum value by considering both possible configurations of the subarrays, one where the first subarray has length first len and the second has second len, and the other where their lengths are swapped. To achieve this, it calls the helper method maxSum, which performs the heavy lifting. Inside maxSum, we first calculate the prefix sum array, which helps us quickly compute the sum of any subarray. The prefix array is built iteratively, where each entry at index I+1 contains the sum of all elements up to index I in the original array. Next, we calculate maxL, an array that stores the maximum sum of an L-length subarray ending at or before each index. For this, we use a sliding window approach, comparing the sum of the current L-length subarray with the maximum found so far. Similarly, we construct maxM, which stores the maximum sum of an M-length subarray starting at or after each index. This is done in reverse order to ensure we capture all possible subarrays that come after a given index. Finally, we combine the results from maxL and maxM to compute the overall maximum sum of two non-overlapping subarrays. By iterating from index L1 to NM, we calculate the sum of the best L-length subarray ending at or before the current index and the best M-length subarray starting immediately after. The maxSum variable keeps track of the highest sum encountered during this process. Once the loop completes, we return maxSum, which represents the maximum sum of the two subarrays in this configuration. This approach ensures we explore all valid combinations of the two subarrays efficiently while maintaining their non-overlapping constraint, thanks to the use of prefix sums and pre-computed maximums. To solve this problem, the first step is to calculate the prefix sum array, which will allow us to efficiently compute the sum of any subarray later in the process. The prefix sum array starts with an initial value of 0, and each subsequent value is the cumulative sum of the elements in the input array up to that point. For example, with nums equals 1, 0, 3, 9, 2, 5, 7, we start by setting prefix 0 to 0. Then, for each index, we add the corresponding value from nums to the sum so far. Prefix 1 becomes 1, prefix 2 remains 1, prefix 3 is 4, and so on. By the end of this step, the prefix sum array is 0, 1, 1, 4, 13, 15, 20, 27. This array will be crucial as it enables us to calculate subarray sums in constant time by subtracting two appropriate prefix values. Now, with the prefix sum array ready, we move on to calculating maxL, which represents the maximum sum of a subarray of length first len ending before or at each index. For first len equals 2, this involves finding the maximum sum of all subarrays of length 2 up to each point. For instance, at index 1, the subarray is nums 0:2 equals 1, 0, and its sum is 1. At index 2, the subarray is nums 1:3 equals 0, 3, and its sum is 3. We continue this process, comparing each sum to the previous maximum, and populate max L as 0, 1, 3, 12, 12, 12, 12. Next, we compute max M, which tracks the maximum sum of a subarray of length second len starting at or after each index. For second len equals 3, we look at subarrays like nums, for :7 equals 2, 5, 7, whose sum is 14, and nums, 3:6 equals 9, 2, 5, whose sum is 16. As we move backward through the array, we update max M by taking the maximum value encountered so far. This gives max M equals 16, 16, 16, 16, 14, 12, 0. With max L and max M computed, we now combine these results to determine the maximum sum of two non-overlapping subarrays, one of length first len and the other of length second len. We iterate through the indices, calculating the sum of max L at the current index and max M at the next index. For example, at index 1, max L, 1, is 1 and max M, 2, is 16, giving a sum of 17. At index 2, max L, 2, is 3 and max M, 3, is 16, resulting in 19. At index 3, max L, 3, is 12 and max M, 4, is 14, producing 26. By continuously updating the maximum encountered so far, we find that the highest possible sum is 26. This completes the first example. Moving to the second example, nums equals 10, 5, 2, 6, 8, 1, with first len and second len both equal to 2, we repeat the same process. After calculating the prefix sum as 0, 10, 15, 17, 23, 31, 32, max L is 0, 15, 15, 15, 15, 15, and max M is 15, 15, 15, 15, 9, 0, the maximum sum of two non-overlapping subarrays is found to be 23. In the final example, we consider an edge case with nums equals 5, 2, 3, first len equals 1, and second len equals 1. Here, the prefix sum array is 0, 5, 7, 10. Since both subarrays have a length of 1, max L is simply the maximum value encountered up to each index, resulting in 5, 5, 5. Similarly, max M reflects the maximum value starting at each index and is calculated as 5, 5, 0. Combining these, the maximum sum of two non-overlapping subarrays is 10. This demonstrates how the solution adapts to different scenarios, including smaller edge cases, ensuring correctness and efficiency in all cases. To analyze the time complexity of this solution, let's start with the prefix sum calculation. Here, we iterate through the entire input array, nums, one time to compute cumulative sums and store them in the prefix array. This operation takes n time since we perform a linear scan. Next, we build the max L array, which stores the maximum sum of any L-length subarray that ends before each index. This requires another single pass through the array, which also takes n time. Similarly, to build the max M array, which tracks the maximum sum of any M-length subarray starting at or after each index, we perform one more linear pass. Therefore, the time complexity for this step is also n. Now, let's look at the step where we combine the results. To calculate the maximum sum of two non-overlapping subarrays, we iterate through all valid positions where the L-length subarray ends and the M-length subarray begins. This requires another n pass through the array. Additionally, since the function computes the result for both orders, first considering L before M, and then M before L, we make two calls to the maxsum function. Each of these calls involves n operations, so the total time complexity is effectively 2*n, which simplifies to n. Moving on to space complexity, the prefix array requires n space, as it stores cumulative sums for the input array. The max L and max M arrays also each have a size of n, so together they contribute an additional n space. In terms of other variables, the solution uses a few auxiliary variables such as maxsum and loop counters. These require constant space, or O1. When we sum up all space requirements, the total space complexity becomes n. Now, comparing this optimized approach to a brute force solution, we can see the efficiency gains. A naive approach would involve iterating through all possible pairs of L-length and M-length subarrays, checking for overlaps, and calculating their sums. This would take n squared time just to iterate through pairs, and an additional L plus m time to compute each subarray sum, leading to an overall time complexity of n squared asterisk L plus m. In contrast, the optimized approach, which uses prefix sums and pre-computes the max L and max m arrays, eliminates redundant calculations. This reduces the time complexity to n, which is far more efficient for large inputs. Finally, let's consider the best, average, and worst-case scenarios for this algorithm. Regardless of the distribution of values in the input array, the algorithm performs a fixed number of linear passes over the array. This means that in all cases best, average, and worst, the time complexity remains n. To confirm this mathematically, we observe that the algorithm processes the input array in a constant number of steps, calculating the prefix sum, building the max L and max m arrays, and combining the results. Each of these steps takes n, and even though we compute results for two different orders, constants are ignored in big O notation, leaving the time complexity as n. Similarly, the space complexity is dominated by the prefix, max L, and max m arrays, which each scale linearly with the size of the input. This confirms the space complexity as n, making the solution both time and space efficient. When solving this problem, there are a few common mistakes to watch out for. First, you need to ensure that the two subarrays are not overlapping. If you accidentally select subarrays that share indices, your solution becomes invalid, so always verify that the indices don't intersect. Another mistake involves incorrect usage of the prefix sum array. If you miscalculate or improperly initialize it, you might end up with errors, especially in edge cases where a subarray reaches the beginning or end of the array. This can lead to out-of-bound errors or skipped sums. Additionally, while brute force may seem like an easy option, it's computationally expensive. A naive n-cubed approach that checks every possible pair of subarrays might work for small inputs, but it will result in time limit exceeded errors for larger arrays. Finally, remember that the two subarrays don't need to be consecutive. Misunderstanding this and assuming they must be adjacent could limit your solution unnecessarily. Now, let's address edge cases and some interview-specific tips. For example, if the input array is smaller than the combined lengths of the two subarrays, the result should naturally be 0 or an appropriate error. Ignoring this edge case could lead to incorrect results. From an interview perspective, this problem is a great opportunity to showcase your understanding of key patterns like prefix sums and sliding windows, which are frequently tested in range sum problems. A good strategy is to start with a brute force approach, then discuss optimization trade-offs with your interviewer before implementing a more efficient solution. Also, pay close attention to edge cases, such as arrays with all negative numbers or arrays smaller than the required subarray lengths. Lastly, be explicit about how you ensure that the two subarrays do not overlap. This logic is critical to solving the problem and demonstrating your thought process. This problem also connects to several related problems that can help you strengthen your skills. For instance, LeetCode 560, subarray sum equals k, focuses on using prefix sums to find subarrays that meet a specific target. Similarly, in LeetCode 974, subarray sums divisible by k, you use prefix sums to solve a different type of subarray property. Another useful problem is LeetCode 238, product of array except self. While this isn't specific to range sums, it introduces efficient techniques for working with arrays without nested loops. Lastly, LeetCode 1231, divide chocolate, involves binary search on the maximum sum of subarrays. This is particularly helpful for understanding how to divide arrays into ranges while optimizing a specific criterion. These problems are great practice to enhance your understanding of range-based techniques and optimizations. Finally, let's explore some alternative approaches to solving this problem. One effective method is combining sliding windows with prefix sums. By pre-computing the prefix sums, you can optimize the process of calculating the maximum sum for fixed-length subarrays, reducing the time complexity to n. The trade-off here is that you'll need additional memory for the prefix sum array. Another approach is dynamic programming, where you define states to represent the maximum sum achievable with subarrays of fixed lengths at specific positions. While this can reduce redundant calculations, it's more abstract and can be harder to implement or debug during an interview. For advanced scenarios, you can even use segment trees to dynamically calculate range sums. However, this method is rarely necessary for interview problems and comes with a high implementation complexity. Each of these approaches offers unique advantages depending on the constraints and requirements of the problem. Great job reaching the end. To summarize, we discussed how to solve LeetCode problem number 1031 efficiently using sliding windows and prefix sums. We also highlighted key takeaways, such as the importance of handling constraints like non-overlapping subarrays. Keep practicing these techniques, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!